4.1, antiderivatives and indefinite integration. So we have done differentiation, so we are going to do the antiderivative, which is the inverse function. So addition, what's the inverse function to addition? Subtraction. Multiplication. Division. Finding the derivative is finding the antiderivative or the integral, as we will eventually just call it. We'll just find the integral. So we've done derivatives. We've worked on them all semester. We are now going to the antiderivative and the purpose behind it. So a function f is an antiderivative if f on the interval of I, so just f on the interval of I, if f prime equals f of x for all x in the interval. So it says find the function f whose derivative is f of x equals 3x squared. So that's the derivative. What was the function?
X cubed.
X cubed? How did you get that?
Because it's 3x.
Because it's 3x. So this function was originally x cubed.
Oh, so
You're going backwards. So you're doing the inverse operation. So you're going backwards. So the question you're asking yourself is, where did it come from? Now, we are going to have rules and definitions and all of that as we get going. Okay, just like we did for derivatives. But a lot of it is what was the derivative. Okay? So note that f is called the antiderivative, capital F is called the antiderivative of f rather than the antiderivative of f. So these are capital F's here, so they are the derivative. So all of those could possibly be the antiderivative to 3x squared. So, I'm sorry, these are the original functions. Would these all not give you 3x squared if you found the derivative?
Yes.
Okay, so what's different about every single one of these?
That one has nothing. That one's minus 5, that one's plus 97.
So that's plus 0, minus 5, plus 97. So this would be what known as what in a function?
0.
A constant? Yes? Because what is the derivative of a constant? 0. So could there possibly be any constant tacked onto anything?
Yeah.
Yes. So what we will do is we will find where it came from, and then we will put plus C.
So we don't put a number, we'll just put plus C?
Yep. We will find that number on some things, but until we do that, it's plus C. Okay? Does that make sense? So it's just like if I gave you a point, I would be able to, like if I gave you, if we said this is the antiderivative, and I gave you the point 7, negative 6, could we solve for it? I have y equals x cubed plus c, and I gave you 7, negative 6. Could I solve for c?
Yep.
Yes, because it would be negative 6 equals, isn't it 343? Plus c. So minus 343. So c would be negative 349. So y would equal x cubed minus 349. So if they give you the information to do it and ask you to find c, then you find c. Okay? But if they don't, you don't. You just put plus c. Make sense?
Yep.
Okay. Nothing changed except that bottom one popped up. Representation, we just went over it. What do we put on everyone? Plus C. So that would be the derivative. This would be the antiderivative. So you go back and then plus c. There's a lot of words there. I'm trying to think. What do you want on there? Okay, using theorem 4.1, you can represent the entire family of an antiderivative function by adding a constant to the known antiderivative. For example, the function d sub x, x squared equals 2x, so that would be the derivative. We can represent the whole entire family by just putting a what with it?
C.
Plus c. So this is called a general solution. This is called the general solution. It's the general solution of the differential equation. A differential equation in x and y is the equation that involves x and y and the derivatives of y. For instance, y prime equals 3x, y prime equals x squared plus 1. Those are differential equations because they have what in them? What does y prime stand for? Derivative, right? Okay. When you guys were asking me about the math classes that I've taken, differential equations was one of them. So we found them, solved them, dealt with them. You will deal with very basic ones. Okay, find the general solution of y prime equals 2. So where did it come from?
2x.
2x. So, there it goes. Oops, sorry. So y equals 2x plus c. And where'd the x come from, guys? The antiderivative, because it was 2x originally, yes?
Yeah.
Now, c can still be 0. So they have an example if you were to graph these general solutions. This is if -1 was c. This is if 0 was c. This is if c was 2. So what's going to happen is c is going to be your x-intercept. I mean your y-intercept, yes? Y equals mx plus b in this case. So is c not your y-intercept in any polynomial? Is the constant your y-intercept? Think about it. Because I find a y-intercept by plugging zeros in for x, yes?
Yeah.
So this c, -7, would be your y-intercept. So what's going to change is your y-intercept. So it basically can move the graph up and down. Okay? So when solving a differential equation, the form dy dx for f of x, it is convenient to write the equivalent differential equation. So we will need to rewrite them. The operation in finding all solutions of the equation is called anti-differentiation or indefinite integration or just integration. We'll use a lot. It is denoted by an integral sign.
What's it called?
This is the integral sign.
What's it called?
Integral sign.
Just integral sign?
That's what that is.
Is there a name for it?
That is the name, integral.
That's not a name.
This, and it's really easy. It's just a
They call it
Charlie.
Charlie.
Okay. It's just an integral. That's what it is. Find the integral. Just like when I say multiply, you put parentheses, yes? Okay. The general solution is denoted as the integral. So we have y equals the integral of f of x dx. because you are integrating a derivative, so the dx is there, would equal the antiderivative plus the constant. Now, right now, we're going to read it as the antiderivative of f with respects to x. Like this statement, you would say find the antiderivative of f of x with respect to x, because it's the dx that tells you what you were differentiating. If you guys just start calling it integral, I don't care. It's not a secret. Like, in a week, it will be an integral to us all the time. Does that make sense? If you just say find the integral, but know that antiderivative means find the integral. Does that make sense what I'm saying?
Yeah.
Integral is so much easier to say than antiderivative, I think. Okay. We good? Okay. That's basic integration. The inverse nature of the integration and differentiation can be verified by substituting f prime of x in for f of x in the indefinite integration definition to obtain. And then you can check it. I know you guys won't. If I say this is the antiderivative, if I find the derivative, should I get what I had?
Yes.
I should be able to move back and forth and get it. When you're done, you need, at least in your head for a little bit, you should check it. There'll be simple ones that you can check. We won't be doing the chain and the product and the quotient at first. Okay? I mean, when I say at first, I mean today and tomorrow. It goes pretty quick because we should already know those things, so you kind of jump in. Like, they took a long time to teach you multiplication, yes? And then they said, oh, we're going to divide today. And then you just started dividing because your multiplication taught you to your division, correct? So it's the same stuff. So this is on page 250. I am not going to sit here for you to write this down. What do I have here? What is on the left? What does it say at the top? Okay, differentiation rules. Did I tell you should have a sheet somewhere that has your differentiation rules on it? Yes, hopefully you have it. What I have here is basic derivative of a constant is 0, yes? Okay. Of k times x is just k because the power is 1. This one just tells you to do that. Should you have any of those written on your sheet? No, because those are the very basic integration, differentiation. You should know those. But then I have this one probably shouldn't either. It just means the derivative of f plus or minus the derivative of g, right? Just, again, a basic. But then I have the power rule. And then you probably would have on your sheet, it's not listed here because we're not going to differentiate with it right away. But you should have the product rule. I would assume you have the quotient rule. I assume you have the chain rule, and then all of your trig ones. Yes? I personally, on any sheet I ever make, is I have basic rules up here, and down at the bottom I have a special trig. Because trig have nothing to do with the rest, do they? They're the trig. So, if you look at these rules, they are lined up. I have the differentiation rule. I have the integration rule. I have the differentiation rule. I have the integration. When you get good at these, because you will, and I expect you to rewrite the sheet every time I add a new chunk to it. The reason for that, does it solidify what you already have in your brain?
Yep.
Yes. If I write this rule, erase, I got a bunch of junk here. If I write this rule, look at this. Isn't it basically the same rule? But backwards. So when you get good at these, you will write one rule and know that this way is the derivative and this way is the integral. So this is on 250. If you don't want to write it down, you should already have that. This bottom chunk is all your, what? All your trig. Now look over here. The derivative of sine is cosine, yes? So the antiderivative of cosine is sine plus c. Can't you just go backwards and add a c? Can I go backwards and add a c? But what's different? This one says negative sign and this one says what? Positive sign. So if it's positive, it was a negative, right? If this is negative, then it was a positive. So you will be using these all the time. So that integration sheet, differentiation sheet, integration sheet, is it important to have? Yes. Now, I honestly don't think any of these should be on it. Should you be doing those in your sleep? Yes, that you should be. But if they're there right now, that's fine. Towards the end of the year, I let you use the differentiation integration sheet every single test. But those cannot be on there. Why?
You should know them.
Right. And neither should the product or the quotient or the chain. Why should the product, the quotient, or the chain?
You need to know them.
You need to know them. Those are ones you have to know. Okay? Now that I've got my soapbox. Describe the antiderivative of 3x. So, what we do is we write the integral of 3x dx. Any constant, 3 is a constant, yes? Kick it out. A multiplicative like constant, not a plus. Does that make sense? So we can take 3, the integral of x dx.
So then you just get rid of.
So there's a 1 there, yes? There's a 1 there. When we took the derivative, we subtracted 1.
What if there was a 2 there?
Huh?
What if there was a 2 there?
Well, we subtracted 1 from 3. Does that make sense? Like when we took the derivative, we subtracted 1. So to find the antiderivative, we are going to add 1. Okay? So what we're going to do is we are going to, we're going to add 1, so it's going to be x squared, yes? But, is there anything right here?
1.
So if I had the derivative of that, you would have 2x to the first, yes?
Yeah.
But I don't have a 2 there, do I?
No.
So where'd the 2 go?
Back.
How did 2 become 1? So 1 here.
-1.
Nope.
-1.
This is multiplication. How did the 2 become a 1? Divide by,
1/2.
or multiply by half, yes? Does that make sense?
No.
Okay. So, right here we have the 3. We pulled the 3 out, yes? And you have a 1. So, I have x to the first, which was x squared. But if I found the derivative of x squared, wouldn't it be 2x to the first?
Yeah.
So I need to get rid of the 2 to make it a 1, so I have to divide by 2. And then plus, see? So then I have 3/2 x squared plus c. And this is the what solution? General. It's important you know that because your directions are going to say find the general solution, find the specific solution. So you need to know. Now, technically, this 3 is in front of all of this, yes?
Mm-hmm.
And so I would distribute it to both. But what's 3C? Is that still a constant?
Yep.
Yeah, so we're just going to put C. We're not going to put 3C because it's still a constant. Does that make sense? So any type of constant, no matter if it's like 3C plus 7, is that still a constant? Yes. So anything like that, we're just going to write C. Am I clear on what I'm doing? Because this would distribute to anything that had an X, but once it distributes to the constant, it's just a C. Okay, so we're going to rewrite, we're going to integrate, and then we're going to simplify. When we did derivative, did we rewrite, find the derivative, then simplify? Yep. Okay, so first of all, we didn't differentiate with 1 over x cubed, so we're not going to integrate with 1 over x cubed. What are we going to change it to?
X to the negative?
Mm-hmm. X to negative 3 dx. Because we're integrating with respect to x, right? So, when we differentiated, we subtracted 1, multiplied by it. Yes?
Yes.
Okay, so we multiplied it and then we subtract. This time we're going to add and then divide, if you didn't notice on the last one. So I'm going to say it again. Derivative, we multiplied, then subtracted. Here we're going to add, then divide. Am I doing it backwards? Yes. Is that what we do when we solve things? We do the order backwards? Yes. Okay, so add 1. So add 1 would be what? Negative 2. And then divide. Plus C. And then simplify, because we don't want things like that. That's gross, right? So what's that simplify to?
Negative 1/2 x.
How about just,
Negative
you're close.
negative 1 over x squared.
Yep,
And 2x.
2x squared plus C. Again, when we found the derivative, we multiplied, then subtracted. Now we're going to add, then divide. Do you get how you're undoing the operation?
Yep.
Okay, so how am I going to rewrite the next one?
One half x.
How about x to the 1/2?
Sure.
Is that what you meant?
What did I say?
1/2 x.
Yeah.
Okay. So add, then divide. Yes? Okay. So what's 1 plus 1/2?
1 1/2.
So 3/2. Well, when we divide by 3/2, we multiply by
The reciprocal.
the reciprocal. Do I need to write this out?
No.
Okay. So I multiply by the reciprocal of that. So it's going to be 2/3 x to the 3/2 plus C. Not too bad so far, right? Okay, so we're first going to do what with that 2? Kick it out, right? Kick it out. Well, not really kick it. You know what I mean, right?
Take it out.
So the integral of the sine of x dx. So you look at your sheet, and it says the integral of sine is negative cosine. That's on that page 250, guys. You're going to need to write those down, right? Okay. So on page 250, I'm looking at it says the integral of sine of x dx is negative cosine of x. That's what it says. Okay. So I have 2 negative cosine of x plus c. Always the plus c, right? So now what? Simplify it.
Yeah.
So negative 2 cosine of x plus c, because technically the 2 goes into both, yes? So if you had more things, because we could do this with like 5 things strung together, right? We just do them independently. So just like we differentiated with, if it was just plus and minus between them, we just differentiated each term, right? So if it's plus or minus here, we're going to integrate what? Each term. We just haven't had that yet.
Okay.
So after we rewrote, what did we do in this section other than the trig one? We added one and then divided.
How do I know what I'm dividing?
You add, then divide exactly what you have up here. So we divided by negative 2. We added and got 3/2, so we divided by 3/2.
Always?
Always. Add, then divide. For the basic rule. Okay?
Okay.
That is right here. Right here. It's the power rule. Because the power rule is the basic. So let's look at it. It has x to the n. So it has x to the n plus 1 added. And then divided by your x plus 1. Okay? So this is your basic power rule. And this was your basic power rule for differentiation. Okay? Okay. Just dx. So basically, this is the integral of 0 dx. So what gives you 0 on a derivative?
Constant.
A constant. So the answer to this is just C. Oh, but I told you completely wrong. It's not 0 because there's a dx there. What's in front of dx?
1.
1. Sorry. If it was 0, it would be nothing, wouldn't it?
Yep.
I'd have to say 0 dx. Sorry, guys. If it said 0 dx, it would be constant, yes? There's a 1 there. So what's 1? X. So it's x plus c.
I thought. Never mind.
Because if it was the integral of 0, it would say 0 dx.
I thought 1 would be a constant.
So if I have x and find the derivative of it, isn't that 1?
Okay.
Because this would be, and I'll write it like this. We can think about as x to the 0 dx. This might help. So add 1 and divide. So x Does that help?
Yeah.
Okay. So the next one I have the integral of x plus 2 dx. And you should have parentheses around that because you're integrating the whole thing. So when we think about it, it's just like when the addition subtraction rule for derivative. We have the integral of x dx plus the integral of 2 dx. So before we start, the 2 should go where? In front of the integral, right? It doesn't have to, and you won't do it after a little bit. So I have the integral of x dx plus 2, the integral of dx, or 1 dx. Yes?
Yeah.
Okay. So the integral of x dx, so add 1 and divide, plus 2 times, what did we just say this was?
1.
What did we just say the derivative of 1 is, or the integral of 1 is?
Oh,
X plus c. You notice I only put 1 plus c, yes? Now, this is why, because there's a plus c here. But if I have a plus c and a plus c, don't I still have just 1 c?
Yeah.
Yeah, you still have just one constant because you would combine them. So you just put c one time. Make sense?
Yeah.
Okay, so probably want to simplify this a little bit. 1/2 x squared plus 2x plus c.
Yeah.
Now, if I was integrating or differentiating, would I leave the 1/2 there? I would factor it out, wouldn't I? Okay. So if I factor out the 1/2, so I'd put over 2, right? That would give me x squared. And when I divide by 1/2, I'm multiplying by 2. So the 1/2 would reduce out, and the 2 would become a,
X. 4.
yes? Now, do we have to do this?
No.
No. When we do some other things, that might be helpful from time to time. Okay?
Why did we put the 2 in front of the integral, the signy thing?
Because it's a constant. You don't have to, though. You could have just integrated this and known it was going to be 2x. I'm just showing you. We did that with the 2. Like, if there was more things, would we factor out any constants to make our number smaller? Yes?
Yeah.
Okay. So you can factor out the 2 or you don't have to. But I'm going to tell you at a certain point, you're always going to factor out anything you can at the beginning because then it will make this stuff smaller. Because we're going to have rules, like we're going to have substitution by parts. You don't want huge numbers running around in there if you can avoid them. Okay, so what do you think we're going to do this one different? Anything?
No.
No, we're just going to do it how many times?
3.
3. So when we first differentiated, we wrote our ddx, 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 right? And then we just started doing it without writing it out. So today we're writing it all out. Probably tomorrow I will quit this step. Clear?
But which one?
This one. I won't keep writing it. But if you want to, you can. Okay? So I have the integral of 3. It's 3, the integral of x to the 4th. Where'd the 3 come from? The 3x. Okay? Dx. Minus 5, the integral of x squared. Where'd the 5 come from?
The 5x.
The 5x squared. Plus, I keep forgetting the dx. Don't forget the dx. Plus the integral of x dx. So I do this how many times?
3 times.
3. So add 1, divide. So 3 times x to the fifth divided by 5. Can I just write that 3/5 x to the fifth?
Yeah.
Yes. Minus, add 1, divide.
3.
So x cubed over 3. So negative 5/3 x cubed. Plus
Squared. X squared. 2. 1/2.
1/2, because you have to divide by the 2, right?
Yep.
So 1/2 x squared. All of it, what? Plus c. Step by step. Rewriting is important. Now, what would you do with this one?
I don't even know.
That's a
Rewrite it.
tomorrow question.
Wouldn't you divide both of them? Wouldn't it be this? Yes? Isn't that what that says?
Yeah.
Yeah. And then so I'd subtract 1/2. So I'd have x to the 1/2 plus x to the negative 1/2. And then I would find the integral. Okay, so get as far as you can and we'll finish notes tomorrow.
Okay.
But please do